There is a pumping lemma for context-free languages analogous to the pumping lemma for regular languages. The goal of this lecture is to state and prove this lemma, which is naturally more complicated than the pumping lemma for regular languages, and then use it to show certain languages are not context-free. Let's review the pumping lemma for regular languages. It said that any sufficiently long string W in a regular language has some short, non-empty piece near the beginning that we could pump. That is, we could repeat it as many times as we liked, including 0 times, and the resulting string would also be in the language. We found the string to pump by looking for the first state to repeat as a finite automaton processed its input W. The pumping lemma for context-free languages says that we can find 2 pieces in any long string Z and pump them in tandem. That is, we can repeat each of them I times for any I equal to or greater than 0, and the result will be in the same language. We'll also see that these 2 strings are close together in Z, and one can be empty, but not both. Here's the statement of the pumping lemma for context-free languages. We can see it as the same sort of game with an adversary that we talked about in connection with regular languages. For every context-free language L, that is, you get to pick L, presumably the one you want to show isn't really context-free, there is an integer n. This is something the adversary gets to pick, but once it's picked, it's fixed for the rest of the game. Such that for every string Z in L of length at least n, and here you get to pick the Z to focus on, you can break Z into 5 pieces, U, V, W, X, Y, such that 3 things are true. The adversary gets to pick how Z is broken, but subject to 2 constraints we'll see in just a moment. And incidentally, V and X are the substrings that get pumped. The first constraint is that the middle 3 components, V, W, and X, are short, no longer than the length of n put together. Remember that V and X will get pumped, so that says not only are they short, but they appear within a bounded distance from each other within Z. The second condition that the adversary has to respect is that V and X cannot both be empty, although one can. And if all the above is satisfied and L really is context-free, then for all integers I equal to or greater than 0, U, V to the I, W, X to the I, Y is also in L. We win the game and prove L is not context-free by allowing the adversary his choices of n and the breakup of Z subject to the constraints 1 and 2, and then picking an I such that U, V to the I, W, X to the I, Y is not in L. The proof of the pumping lemma for context-free languages starts with a Chomsky normal form grammar for L. Technically it is for L minus epsilon, but the empty string will never meet the condition of being of length at least n, so its presence or absence doesn't matter. This CNF grammar has m variables for some m, so we're going to let n be 2 to the m. And now let's consider any string Z in L of length at least n. That's 2 to the m again. We're going to prove first that any parse tree in a CNF grammar for a string Z of length at least n equals 2 to the m must have a path of length m plus 2 or more from the root to a leaf. We'll actually prove the contrapositive. That is, suppose there is a parse tree Z with no path longer than m plus 1. Such a path has m nodes labeled by variables at the top, or the beginning, and 1 node labeled by a terminal at the end. That is, here is a typical path. It will have variables here, here, and here, and then a terminal there. Okay. If we forget about the terminals at the leaves, a parse tree in a CNF grammar is a binary tree. Thus, at each level, the number of nodes can at most double. Thus, there is only 1 node at the top level, the root. There can be only 2 nodes at the next level, 4 at the third, and 8 at the fourth, and so on. In general, there'll be at most 2 to the power m minus 1 at the nth level. But this tree has at most m levels with variables, and then along each path of variables, the last variable has 1 child with a terminal as its label. The largest number of leaves occur if all the paths in the tree have exactly m variables. If some paths terminate before level m, there will be fewer leaves. Thus, there are at most 2 to the m-1 nodes that are labeled by variables and have a single child with a terminal label, and thus there are at most 2 to the m-1 leaves. Finally, we therefore can conclude that the length of the yield is at most 2 to the power m-1. Now 2 to the power m-1 is n over 2. Since z is of length n, it cannot be the yield of any tree that has paths limited to length m plus 1 or less. Therefore, we conclude that somewhere in the parse tree for z is a path of length at least m plus 2. Now we're ready to prove the pumping lemma. We just proved that z's parse tree has a path of length at least m plus 2. Only the last node in any path can be labeled by a terminal, so there are at least m plus 1 nodes with variables along this path. Let's focus on one of the longest paths in the parse tree for z. Surely there are at least m plus 1 variables along this longest path. Remember that m is the number of variables of the grammar, so along this path there are 2 nodes labeled by the same variable. Call it a. In fact, to make sure we pump short pieces, let's look only at the bottommost m plus 1 variables along this path, which could be much longer than m plus 1. And we know that 2 of them must be the same. On the next slide, we'll see what the parse tree must look like. Here's a picture of the parse tree for z. We've shown the path we've focused on and the lowest repeating variables along that path. The purple tree is rooted at the lower a, and the yellow tree, with the purple tree within it, is rooted at the upper a. Let w be the yield of the purple tree. V and x are the portions of the yield of the yellow tree that precede and follow w, respectively. And let u and y be the portions of z that precede v and follow x, respectively. Let's look at the yellow. Since the path shown is as long as any other, and that path has at most m plus 1 variables, we know by the lemma 1 that we just proved that the yield of the yellow plus purple is no longer than 2 to the power m, or n. That is, the length of vwx is no more than n. But v and x both can't be empty. Why? That's a useful property of Chomsky normal form grammars. Since the 2 a's shown in the tree are different nodes, the upper a must have a child to the left or right of the path shown. That's a consequence of the fact that we eliminated unit production, so all bodies that have variables have at least 2 of them. Moreover, once we have a variable not on the path, there are no epsilon productions, so we must generate from this variable at least 1 terminal. That is all we need to conclude that either v or x or both have length at least 1. Now we can take advantage of the fact that we have 2 a's along the path. We can get rid of v and x by pumping 0 times. That is, we know the purple tree can substitute for the yellow because both trees have the same variable a at the root. If the original on the left satisfies the conditions of a parse tree, that is, every interior node is the head of a production whose body is the labels of its children, then the same will be true of the smaller parse tree on the right. We conclude that uwy is also in the language. Or we could pump twice, that is, replace the purple tree by the yellow, which has the purple within it, and you get a parse tree whose yield is uvvwxxy. And in the previous tree, representing pumping twice, we could again replace the purple tree by the yellow and get a bigger tree whose yield is u 3 v's, w 3 x's, and then y. In the same manner, we can get parse trees for all strings with the form u v to the I, w x to the I, y for any integer I equal to or greater than 0. These strings are therefore all in the language L. That proves the pumping lemma for context-free languages. Let's look at an example of how the pumping lemma can be used to show a language not to be context-free. This language, which involves matching the counts of 2 blocks of zeros, is context-free. A grammar or PDA for it is easy to construct. The ideas are very much like what we saw for the language 0 to the n, 1 to the n. But give the language 3 blocks of zeros, all of which must be the same length, and we're suddenly outside what context-free grammars can do. We can prove that using the pumping lemma for context-free languages. So we'll pick this language L, and the adversary now gets to pick N. We don't know N, but we do know it is fixed for the rest of the game. We get to pick Z, so let's pick 0 to the N, 1, 0 to the N, 1, 0 to the N. That is, each block of zeros is of length equal to whatever N the adversary picked. Now the adversary gets to break our Z up into Z equals UVWXY, but he must choose these substrings such that VWX together are no longer than N, and V and X cannot both be picked to be the empty string. There are two cases depending upon whether the adversary picks V and X to have zeros or not. In the first case, suppose there are no zeros among V and X. Then since they cannot both be empty, there must be at least one 1 among them. But then, if we pump 0 times to get the string UWY, we know that there is at most one 1 in this string. The pumping lemma claims it is in the language L, but it can't be because all strings in L have exactly 2 1s. In the second and last case, V and X have at least one 0 among them. VWX has length at most N, so these three substrings cannot extend from the first block of zeros to the last because N plus 2 positions separate those blocks. So again consider UWY, which if L is context-free must be in L. Removing V and X must leave at least one of the 3 blocks of N zeros intact, so it still has N zeros. But V and X have at least one 0, so in UWY, at least one of the blocks of zeros has fewer than N zeros. We conclude that in this case too, UWY cannot be in L, and thus L cannot be context-free.